Hey, what's going on YouTube? I believe that we should be live any second now. Let's confirm though before we get started. Welcome, y'all. My name is John. If it's your first time here, welcome. It's nice to meet you. I hope you are in for the nerdiest YouTube channel, the nerdiest stream in the world. I am going to literally just be practicing mathematics. Oops, I'm in the wrong account at the moment. All right. So something can always go wrong while live streaming. Things can always go wrong. And I think that I forgot to turn on dual streaming. No, I didn't. Okay, we're good. We're good to go. All right. So today is March 20th. We're going to be practicing eigenvalue, eigenvector problems today, as you can tell. I'm trying to work every single exercise from this book, which is my favorite. It's out of print, so let's all petition to Addison Wesley, the Addison Wesley Publishing House, to reprint this book because it's the best. It's just the best book. I'm working from an iPad, and I've already written down the problems that we're going to be working today. So if you're curious, here we go. First, we're going to, from section 1, just defining eigenvalue, eigenvector pairs. We'll find eigenvalues and eigenvectors for this small matrix. Problem 2, I didn't actually write down the matrix. This happened recently as well, so let me actually write down the matrix for you all. Please, I encourage everybody to actually pause the video and try these problems yourself before we keep moving on and before I do a solution. That way you can learn and you can compare your solution and your way of thinking to mine. And then selfishly, or somewhat selfishly, dude, if you have a different solution than mine, if you feel like you have a cleaner, nicer, simpler solution especially, or just an interesting other solution, dude, leave a comment. Like, feedback is a gift to me, y'all. I am a new teacher. I mean, I've taught many years. I even graded homework in linear algebra a long time ago, but I've never run a classroom in linear algebra, so I'm trying to get some practice. I'm somebody who just really believes in practice, in deliberate practice, and I think that YouTube Live can be a pretty good way, actually, to practice math. So, oops, I don't want that scaling. Scaling, we're talking about scaling a lot. There's an example of scaling. All right, so there's the matrix. I actually wrote it down this time. But what happened to my 7? Where did 7 go? Here we go, -7. Okay, so that's the second section. Then we're going to go to this third section on 2 applications of freaking matrices, or eigenvalue, eigenvector pairs. So, oops, there's a couple little things I wanted to fix here. Do I want that rightmost bit on the screen? Anyways, whatever, who cares? Production quality. I'm always trying to improve the quality of the stream, so any hints, any ideas, let me know. All right, so 2 applications. Here is this problem. So we have this recursive sequence that's defined where we start with 0 and 1, just like in the Fibonacci sequence, and then we take the average of the last 2 numbers. So 1 plus 0 divided by 2 is 1/2. What is 1 plus 1/2? What is the average, the midpoint between 1 and 1/2? Well, it would be 1/4, wouldn't it? What's the midpoint between 1/2 and 1/4? Midpoint between 1 and 1/2, the average of those two is 3/4. That's what I meant to say. And then, et cetera, we keep going in that process. So we're going to represent that as a matrix. and then we're going to find some really cool mathematical properties of this sequence based on applying linear algebra and applying matrices. Okay, so let's get started with the first problem. Eigenvalue, eigenvectors. And then after all that, we might just chill and take some notes, because I haven't yet taken notes on these sections. I'm reviewing a lot of this material, so I just remember it. I remember how to apply this stuff. But in the past, when you're learning it for the first time, you definitely want to take notes before anything else. So, okay, we've got this matrix. So what is an eigenvalue, eigenvector pair? It is a pair of an eigenvalue and an eigenvector such that the matrix is a scaling, like multiplying the vector by this matrix is just a scaling of the vector. So I keep drawing this, and it's because it's a useful example. Like maybe lambda v is just stretching in the same direction. Maybe this is the first eigenvalue eigenvector pair, and maybe the second eigenvalue eigenvector pair might be in the reverse direction, lambda 2 v2. Usually, I shouldn't say usually, but usually there are multiple eigenvalues and eigenvectors. Yo, what's up, Samya? Hi, sir. Can you please clear my doubt? Maybe. Depends on what your doubt is, dude. What's your doubt? How are you? How's your day going?
Okay.
No. Okay. The assistant can be annoying, 15 years later or whatever. Yo, we got somebody in the chat. How's it going, man? How are you? All right. So, what's your doubt, dude? Let me know. I'm happy to try to clear your doubt, but I don't know. Depends on what it is. Depends on what it is, bro. That's way too small. We'll figure out how to make that better in the future. I don't know how to. Dude, streaming is hard. Okay, so anyways, eigenvalue, eigenvector pairs are these properties, and it turns out that all matrices have eigenvalue, eigenvector pairs. I think that's not exactly correct. There are conditions. I think like an invertible matrix, a non-degenerate matrix has eigenvalue, eigenvector pairs. Is a product of slopes two perpendicular lines -1? Well, if you have, this is actually quite relevant. I don't normally take random questions from chat. I don't usually, but that is actually quite relevant to linear algebra. So if I have a line y equals mx plus b, I know that a perpendicular line, well, there are many of them, right? Like, dude, any of these are perpendicular lines, right? So there are an infinite number of perpendicular lines. I'm going to, in particular, take the perpendicular line that goes through the origin. So this is some other equation, m prime x plus b prime. Well, I chose the line that goes through the origin, so when x is 0, b prime is 0, right? Now, note that I drew this line through the origin, but it doesn't have to be. You said any line. So let's actually move it there to be a little more clear. And this got all messed up over here. y equals mx plus b, right? Now, we want to solve for a point where they intersect. So there will be some x where there will be some x such that some x1, y1, or x naught, y naught, such that y naught equals m x naught plus b, and that also equals m prime x naught, right? So the y value is the same for both of them, so I can just focus on the right hand of this equation. And you are saying, your question is a product of slopes of two perpendicular lines -1, a line parallel to y-axis and a line parallel to x-axis, one slope is infinity. Okay. All right. Yeah. You don't want the proof. Well, dude, I am here practicing math. If you ask me a question, I'm probably not going to answer it to begin with because I am here to practice. But you might ask me a question that makes me think of math that I do want to practice. I know that m prime should be the negative reciprocal of m. I know this fact. I know this. I remember it. No, you're not rude. You're chill, dude. You're chill. Most people just don't know what a practice stream is like. So I run a practice stream in guitar, actually. I'm a guitar practice streamer. And usually we don't take questions because we're here working and trying to get something done. But you're actually giving me a good question to think about and go off topic for a second. Like, have I ever shown that m prime is the negative reciprocal? I don't think I have. Let's see if we can try to figure out this. And proofs are math. Proofs, this doubt hasn't been solved by any one of my elders, so I am just curious. You think that you have an unsolved problem that you just mentioned, or something else? And dude, all math has already been solved. I mean, not really. There's a lot of open questions, but this type of math is, this kind of math has been proven for sure. The point is for me to learn how to do it and to get the practice repetition of how to do this. So I want to show, and this is also good for the audience because some people here have never, worked a mathematical proof. How do I show that? And this is also familiar to some people, so this is good. Okay, now you got me on a tangent. Show that m prime is -1 over m. Okay. Well, m prime is going to be m x naught plus b divided by x naught, which is m plus b over x naught. I don't know if this approach is going to work. Why did we get something that looks pretty nonsensical? That doesn't seem to work. Why doesn't this approach work? Oh, you know what the problem is? It doesn't work because in this equation, y naught is 0. Y naught is 0, so we have some problems for where we're kind of dividing by 0, I think, or doing some... We get a mathematical problem right now because I'm Well, no, it shouldn't necessarily be. It is a problem here. It shouldn't be a problem that y is 0, but it is a problem to try to divide by x naught here. So all we... Oh, no. What am I talking about? Why not? X naught, Y naught is not necessarily 0. It's here. At the point of intersection. So now... I mean, this looks good. Y is equal for both of them, and the point of intersection, x naught, should be equal. And I chose the perpendicular line that has y-intercept 0. So the right-hand side is correct. Then, Yeah, I mean, I get to this line, but this isn't a great. I don't know. I'm a little stuck right now. I don't see the immediate proof here. Just use a quadratic formula for all questions. That doesn't work unless you're working with a quadratic. I mean, but we will work with the quadratic equation if I get back to the actual question. Dude, find the characteristic polynomial. We are actually going to use the quadratic equation for this problem. Okay, so take a line which makes angle theta with x-axis, then take another one which is inclined to it at an angle theta at their point of intersection, then the triangle formed by these three lines, x-axis and the two lines. This triangle will have its internal angles as theta, 90, and 90 minus theta. Then the angle of inclination of the second line will be 90 plus theta. So the first slope is tan theta, seconds will be tan 90 plus theta. Nice! Okay, heck yeah. I think I see what you're saying. So, nice job, dude. Thank you. Thank you for quizzing me and stumping me. Alright, so you're saying that we have a line and we have an angle theta, and then we choose another line which is perpendicular, and then because it's perpendicular, how do I know? Well, yeah. So this is going to be theta plus 90 degrees, right? Because this is a right angle. And then this other angle, phi or something, satisfies phi equals 180 minus theta plus 90 minus theta, right? So phi is going to be 90 minus 2 theta. That's not quite what you said, but these should form a straight line of 180. So, yeah. I mean, that's what I'm getting. Angle of inclination of the second is... Oh, wait. Nope. Oops. Yeah. Okay. So the first angle, theta, is there. The second angle, this is horrible, but the second angle, phi, for the second line is theta plus 90. And then, I don't know, gamma or something over here. Gamma satisfies 180 minus phi, which is 90 minus theta, right? Okay, yeah. I'm with you, dude. Then, what exactly, how are we going to use, so we want to look at right triangles that are built here. And, okay, yeah, so I see, so if we look at a right triangle formed on this side, and a right triangle formed on this side, then we have, and we choose a point such that this length is 1 or something, or, yeah, I would say length 1. Then we would have sine theta equals opposite y. Sine theta equals y. Or we could choose some x. Let x be the distance, be some distance, and choose this point negative x. And then we would have I want this to be like y prime, because I don't know yet that they match, right? Then the slope of the second line would equal, the slope is defined as change of y over change of x. So as x increases by the length x, then y decreases by y prime. Then, and similarly, this one would be y over x. Well, y over x is equal to, I think that we need to use the fact that these are perpendicular. So I think that we would want to also be using, we would have to use the fact that they're perpendicular. So we would need to maybe use the other right triangles above, or because we've already proved some properties based on the fact that they're perpendicular, I could be using the fact that gamma is 90 minus theta. Okay, so y prime over x is equal to negative tan gamma, right? Tangent is opposite over adjacent, which is equal to negative tangent of 90 minus theta. And m is tangent of theta, right? M is the slope of the original line, tan theta, and then m prime is tan of 90 minus theta. do we have a formula for tangent? We must have some sort of relation between, we must have some sort of relation between, like the, what's the name for these? Subtraction of angles using tangent. I don't know them off the top of my head, but right now, yeah, let's just look one up. Let's see, how can I don't want to prove this formula, but it's telling me that I should try to learn these. Trig identities. Let's just look up trig identities. And there's going to be one with, let's see some of these. Tan theta. I want the ones that are adding and subtracting pi over 2. Yeah, okay, so this one. Okay, tan. I knew that, yeah, I'd have to look up one of these. I don't know how to prove it right now, but I could figure it out, dude. Tan of pi over 2 minus theta. I could learn this, you know, I could prove this someday, is cotangent of theta. All right? And cotangent, so then here we have 90 degrees is the same as pi over 2 radians, of course. So then the purple lines continue as negative cotangent of theta. Cotangent of theta would be adjacent over opposite. So this is negative x over y. And x over y is, well, this is the same as, I think it's cleaner to say that cotangent of theta is defined as 1 over tangent theta. And tangent theta, we saw, is equal to m. Right? So, voila. Therefore, the slope of a perpendicular line is the negative reciprocal of the first line. Boom! Did it. Yo, somebody quizzed me and I succeeded. Dude, I succeeded. So it intersects with the first one in the first quadrant. Sir, don't take a line which intersects the first one at the origin. Make them intersect in the first quadrant. My way worked. Hey, you admit it, right? My way worked. I got it, dude. I got it. I didn't memorize this proof. I came up with this proof, dude. I'm betting that you memorized that proof. Let's come back to the original doubt. No, dude, I'm going to go back to what I was working on. You're welcome. Though, you're welcome for talking about your question for a little bit. All right, let's get back to what I'm actually here to do. Fraleigh 5.1.4. I'm just going to copy it all over again. All right, thank you for the question, dude. I'm not here to just take random questions, though. You know, I'm here to practice linear algebra. I'm here to study what I was already going to study. No offense. All right, so we want to find pairs lambda and v such that this equation is true. AV equals lambda v. If that's true, then we can subtract from both sides and we'd get, and then factoring out the vector, we'd get this equation. If that's true for a non-zero vector, then the determinant of a minus lambda I is going to equal 0. So this is how we find the characteristic polynomial. We take our matrix and we subtract lambda across the diagonal, because that's what lambda, subtracting lambda I does. We have -5, 16, and we take this determinant. So multiplying across the negative diagonal, and I like to factor out a -1 out of these. We get lambda plus 7. So I factored a -1 from that one and a -1 from this one, right? And then plus 5 times 16, which is 80, right? Now we get back to somebody else's point of the quadratic equation. So I'm going to solve this either using the quadratic equation or by thinking really hard. Either way. 17 times 7. Ooh, that's a good one. Would be 170 divided by 2. What's the best way to show this one? 170 divided by 2 plus 14 is how I see it. Because 17, what I'm doing is 17 times 5 plus 2. 5 is 10 divided by 2. So 17 times 10, and then divide by 2, and then add, 17 times 2. Oops, I'm glad I wrote it out. I thought that for a second. Okay, 34. That's what I meant. 170 divided by 2 is 85. 85 plus 34 is 119. Okay, so we've got lambda squared minus 10, plus 119. Nope, minus 119 plus 80, which is lambda squared minus 10 lambda 39 minus 39. How can I... 13 and 3, right? 13 and 3 would get us this. So lambda minus 13 times lambda plus 3. Boom. There it is. So therefore, lambda 1... I'm going to order them negative and then positive. Lambda 1 is -3. Lambda 2 is 13. Cool. So, the characteristic polynomial is this, which was question A. The real eigenvalues are these. And now the question is asking for the corresponding eigenvectors. So we solve for V1 such that A times V1 equals -3V1. Because again, we are looking at the equation, we're finding these such that AV equals lambda V, right? So first, this is the first eigenvector, and then the second eigenvector, we're going to solve this equation, AV2 equals 13V2. Okay, so AV1 equals -3V1. Well, we can do this by solving the equation -7, -5, 16, 17. Oh, wait. No. Never mind. Then a plus 3I times v1 equals 0. This is what I meant to say. So then a plus 3I would be... Now we're going to be solving this system of equations. So negative 7 plus 3 is negative 4. Here, let's copy this over and just remind ourselves that this is A. So negative, this diagonal in the upper right is the same. 16 in the bottom left is the same. And now 17 plus 3 is 20. And we're solving the system of equations such... Yeah, we're solving this system of equations. Well, this is... this row reduces to 4, 5, 0, and 0, 0, 0. So this corresponds to the equations 4x1 plus 5y1 equals 0 or something. And then if x is 1, if we take x to be 1, then we solve for y in terms of x. Y would be negative 4/5. So there's our first eigenvector. Loon, my cat wants to join, but she's been bad, so I'm not going to let her in. And then, again, let's just copy this over for convenience. Now, let's stick with our yellow solution color. A minus 13I. We're solving this system of equations. So we have this system of equations. Negative 20, negative 5, 16, and 4. Wait. Minus 13. Why does this look super wrong? Oh, no. This looks fine. Yeah, okay. So this is similar to, if I divide the second line by 4, we get that. And if I divide the first line by 5, we get this. So those two lines, those two equations are dependent. So then therefore our solution vector, our second eigenvector, is going to be let's again take x to be 1, and then we can solve that y equals negative 4x. Y is negative 4. So this is a perfectly fine eigenvector 2. Yep. Because, again, these equations correspond to 4x plus y equals 0. And if you choose x to be 1, then y is negative 4, right? Just showing that for others. And I like for these to be integers, so let's multiply by 5, and we get, this is a slightly nicer eigenvector, I think. Okay, so, all right, fine, let's let the cat in. She's begging. Hi, Luna. All right. Cool. Any questions? Any questions? Okay, so now we're done. We found the eigenvector eigenvalue pairs. First, part A, we found the characteristic polynomial, lambda squared minus 10 lambda minus 39. Secondly, and thirdly, we have eigenvalue, eigenvector pairs lambda 1 v1 is equal to, let's really just like remind ourselves of these things, -3 and the vector 5, -4. And the second pair, Luna, you're so cute. The second eigenvalue is 13, and our eigenvector is 1, -4. Okay? Those are our solutions. Whoa! She's slipping. Hey, Luna. Luna, you're so cute. All right, there we go. Thanks. Hope y'all are enjoying my practice stream. Thank you. If you are, please hit the like and subscribe. And yeah, we just finished a problem, so let's take a short break and play a song for you all. I am a classical guitarist as well as a mathematician. So if anybody is curious about that, I also have a secondary stream. I have a secondary channel where I practice classical guitar. So thank you. Let's take a little break. Say hello to this kitty cat. Let's say hello to this kitty cat. Oh, the baby. Oh, look. She's good. She's a good cat. Hello, Luna. All right. It looks like I lost everybody. I apologize. But I don't apologize. I'm here to practice. I'm here to cuddle with my kitty cat. And I'm here to get better at math, the math that I'm studying at the moment. So, hell yeah. What's up? Hell yeah. Hell yeah. Hell yeah. Look at this good cat. Look at this good cat. Oh, the views are going up. She's the views generator. She could tell that the stream was getting kind of boring. Too much math. Not enough cuddling. Hi. Isn't she a good cat? She's a good cat. All right. Let's play a song for you all. Thank you. Thank you for watching. What shall I play? What makes me... What exactly... Here, let's go back. Let's go back here. And let's mute that background music for a second. All right, so this is what we just found. What song makes me think of eigenvalues and eigenvectors? So we have stretching of vectors, stretching. What comes to mind for me in terms of stretching? It's probably stretching a note on the guitar. Tremolo is a technique on classical guitar that attempts to stretch a note. Notice that when we play a note on the guitar, it immediately begins decaying. Like, we don't have sustain on the guitar the way that the violin does. The violin has sustain. So I'm going to try to fake sustain on the guitar by playing tremolo. It's our way to try to pretend as if we were a bowed instrument with sustain. So here, this is Kirkossi Etude 1. Well, I'm completely cold. So that's I'm now going to think of that as the Eigenvector song. That's the Eigenvector song. Thank you, everybody, for indulging me in my stupid, silly hobby of classical guitar. Thank you. So, again, I don't know if I mentioned it. All the music that we're listening to in the background, this is me. This is my fall recital. So, thank you. Let me know in the comments, feedback is a gift. If the guitar segment is annoying, well, I might still continue doing it, but I might not. If people find it annoying, I will stop. Let's keep going. Now we're going to do diagonalization. Here we go. We got this problem. So it's kind of the same thing, but now we have this new concept about diagonalization, which is a cool... Hey, kitty cat jail. Kitty cat jail. Don't scratch the lamp. Kitty cat jail. Don't do it. Your guitar... Thank you. Thank you, dude. Your guitar segment is fantastic. You got great fingers there. I appreciate that. Thank you, man. Thank you. Yeah, I have another channel. You can find a link in the description for my guitar channel if anybody's curious about that. So where did I just put my pen? Where did the pen go? Apple Pencil. Where did that Apple Pencil go? I dropped it, didn't I? Where did it go? How? Aha, here it is. I found it. How are you, Royal Crown? How's your day going, man? How are you? Nice to meet you, I think. Have you been here before? Bro, do you like math? Do you like math, dude? I know I do. Way too much. Way too much. All right, let's keep going. We got another diagonalization, or another eigenvalue problem. So we're solving AV equals lambda V with this bigger matrix. So now we're going to have to do a 3x3 determinant. And again, that means that we're going to find the determinant of A minus lambda I and set that to 0. So we're calculating this determinant, 6 minus lambda, 3, negative 3, negative 2, negative 1 minus lambda, 2. 16, 8, and negative 7 minus lambda. And we want this to equal 0. So I'll say 0 equals this, actually, and on the right-hand side, I'm going to use the special fact of 3 by 3 determinants to immediately write down. So we have this negative slope diagonal plus this slope. 3, 2, 16. I'm just going to leave it temporarily as the numbers. And then negative 3, negative 2, 8. Okay. So we've got all that minus the positive diagonals. I'm going to stop drawing these lines so that this is more readable as we keep working this. We've got, let's see, this as 16 times negative 1 minus lambda times negative 3 plus 8 times 2 times 6 minus lambda plus negative 7 minus lambda times negative 2 times 3. Okay, so this is kind of gnarly. I don't really think that there's a much nicer way to do this. Like, you could try to do row reductions on a 3 by 3 determinant, but when it has variables, I just don't think that a row reduction is really going to make your life any easier. Could be wrong about that. I wonder. Yeah, I mean, I wonder. Because, like, you could zero out maybe this 2 in that column if you, like, add the first column to the third column. Huh. I'm tempted to try it. Because this is a gnarly... That's like a really ugly freaking bunch of simplifications and reductions if you just do it the straightforward way. I wonder if there's a nicer solution if you try row reduction but still keeping the polynomials. Huh. So tempting. It's very tempting, but I don't think I should. Let's not do it. I'm not going to bother. Let's do it the straightforward, good old-fashioned way. I'm going to keep 6 minus lambda, and then if I distribute these two terms, then I have lambda squared plus 8 lambda, right? Lambda squared plus 8 lambda, yeah, plus 7. Plus, what is 32 times 3 would be 96. Plus, 6 times 6 times 8 is 48. Right? Yeah. Minus, here, in the second bracketed term, I would factor out a -1 out of this second term in the product and a -1 from this 3 to see this as 16 times lambda plus 1 times 3, and then 16 times 3 is 48, right? Yeah, 48. So this is 48 lambda plus 48. Here we've got -16 lambda plus 16 times... Oh, wait, no. Let's do it this way. Multiplying something by 16 actually is doubling 4 times. So 16 times 6 is 6 doubled is 12, 12 doubled is 24, 24 doubled is 48, 48 doubled is 96. Right? That's 4 doublings of 6. So, yeah, plus 96. And then we have, again, I'm going to factor out a -1 and -1 so that this is the same as lambda plus 7 times 6. So we have plus 6 lambda plus 42. Okay. It's good for you. It's good for you to do these types of calculations in your head, not with ChatGPT. You don't have to ask ChatGPT for help on everything, dude. You can do these things in your head. It's good for you. It's good for your brain, even if you make mistakes. I'm going to factor out a -1 from all of these terms so that I'm going to treat this as lambda plus 6. And these are minus terms. So I factored out a -1 everywhere. And then what are all the combinations of lambda squared here? We have 8 lambda squared plus 6 lambda squared, which is 14 lambda squared. What are the combinations of lambda? We've got 7 lambda and 48 lambda, which is 55 lambda. And then we have the combinations of the constants, which is 6 times 7, which is 42. If I subtract -96 minus 48 is the same as -100 minus 44. So first I subtract 4, then I subtract the remaining 44. So we get -144. Okay. And all of this is multiplied by a negative, and I don't want to lose that negative, so I'm going to highlight it for a second. Now, this Combine our lambdas is 38 lambda. 48 plus 96 is 144. 144 plus 42 is 186. Okay, so I'm finding my lambda cubed terms. Let's find our lambda squared, our lambdas, and then our constants. So this one's the only lambda cubed in this whole expression. Then we have minus 14 lambda squared minus 38. Oh, wait, no, that's the only lambda squared term. So this will be a positive 14 lambda squared. Oh, wait, no. Sorry. I already distributed the negative. Minus 14 lambda squared. Yeah, I already distributed the negative. And then we have negative 55 minus 38 lambda, which is negative 93. Negative 93 lambda. And our constants, we have 144 minus 186. Which is negative 42. Yep. Holy moly. Isn't this a tricky one? We're getting into some gnarlier calculations here. That's a negative, so let's make this okay. Okay, what is a vector? Good question. Thank you for asking something that I can explain a little more simply. A vector is a thing with a length. It has some amount of length, and it also has an angle. That's one way to think of it. This is kind of a way to think of it. I think of physics. You use them in this way all the time in physics. But you can also think of a vector as just a list of numbers in some vector space. Like in the real numbers, this is a list of numbers, and you can add and subtract and you can multiply a vector by a constant. Maybe K and L or something. D, E, F. Like I can add these vectors together to equal. I add the first components together. So first I multiply every component by that scalar. And then I add the first component of the second vector. This is a little messy right here. I apologize. I should have done it in 2 steps. KA, KB, KC plus LD, LE, LF. And then you add each of the first component of each. Bizarre how Luna is non-existent when strings are not being strummed. She begged. She was like pawing at the door earlier, and then she scratched the lamp, and now she's in kitty cat jail again. But what's up, Rusty Shackleford? Yes, a vector is a 1D matrix. That's absolutely 100% correct. A vector is, so a 1D matrix. It's a vector is, it's like a matrix with 1 row and n columns. Yes, that is true. Like A1, A2, ... AN. Yes, it's like it's a list of numbers, and then any tips for a newbie learning linear algebra? Show up here, man. Ask me questions. The best, like, if you are curious about this, right now we're in chapter 5. Tomorrow I'm going to do chapter 6, then I'm going to do chapter 7, then I'm going to do chapter 8. But then here's the cool thing, dude. When we restart, I'm going to restart, and I'm going to do 1, 2, 3, 4, 5, 6, 7, 8. Then we're going to get all the way to 9, and we're going to restart. And then I'm going to do chapter 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we're going to get to chapter 10, and we're going to restart again. So, dude, literally, if you want to learn linear algebra as a newbie, go watch my chapter 1 videos. You know, just go watch like a few of the chapter 1 videos until you feel like you get it. Then you could watch my chapter 2 videos. Then you could watch my chapter 3 videos. So this way of working in computer science, we call it breadth first. I take one problem from the first chapter, one problem. Well, yeah, I'm solving the next problem from every section. I'm not going depth first in one section, like solving all the problems in one section before moving to the next. Yeah, breadth first search, layer by layer. Exactly. Yeah. That's exactly it. I'm doing breadth first search. It's kind of like I'm spiraling, though, like doing more each time. So it's like breadth first, I visit this node, then I visit this node, then I visit this node again, then I visit this node, then I visit this node, then I come back to this node. You know what I mean? Like it's just like a little bit different than breadth first search. It's like a spiral kind of, but it's essentially the same thing. It's essentially the same thing. We're doing a breadth first search on, or breadth first approach on solving all the exercises in the book. So that means that we're going to be doing this book for a long time because there's like 50 problems in section 1. So that means like 50 restarts, which is kind of cool, I think, as an idea. What do you think of that idea? Do you like that? Then, yeah, if you want to learn linear algebra, just go watch some of my chapter 1 videos, dude. Okay, anyways, let's get back to our Sudoku puzzle that we're working right now. A little bit tedious, I know, but hey, it's good for your brain to do this stuff by hand sometimes. Yeah, okay, so, well, we did get to this part. So let's zoom in and focus here. How can I factor a third degree polynomial? Some people know this, not everybody, but you can do synthetic division and try to, essentially we have long division of polynomials. We have a division algorithm for polynomials, the same way we do for other things. For numbers, I'm saying. We have long division of numbers. We also have division of polynomials. I don't know, dude. If we have... Let's see. Notice that if we have a positive number, then every term is going to be negative. So it can't be a positive number, right? Because then every term would be negative, and we want to solve for some factorization so that we have lambda minus a root, and then we have lambda squared plus dot dot dot, right? So our root has to be negative to make this polynomial 0. If we have a... I don't know. Let's just guess. Let's just guess something. What about -2? So how does division of polynomials work? You drop the first, you multiply the thing on the left with the thing down here, and then put that in the next entry. And then you add -14 plus 2 is -12. -2 times -12 is 24. This didn't work. So then this is... yeah, this one didn't work. -93 plus 24, -69. Yeah, this didn't work. -2 times -69 is going to be more than... It's going to be like around 140, and these two added together is not equal to 0. So, that means... I think that was a too large of a number, right? Ah, geez, do we have... Okay, what else do we have? Let's just try -3. We have the rational roots theorem as well that says that if we have a rational root, A over B, then A divides -42 and B divides -1. So 42 has 2 as a factor. It also has 3. And, well, the only divisors of -1 are positive and -1. So at least if we have a rational root of this polynomial, which I hope so because we're solving an eigenvalue problem by hand, then it should be an integer. We tried -2, which is a contender. Let's try another one. -1, -14, -93, -42. If this doesn't work, then I'm going to suspect that I made a typo somewhere. So, or I've forgotten how synthetic division works. Those are both possible. -3 times 9 is -27. Again, this didn't work. Shoot! Oh, wait. Slow down, John. Slow down. -14 plus 3 is -11. What am I talking about? Okay. -3 times -11 is positive 33. I mean, this still didn't work, but... Yeah, because this is -60. -3 times -60 is 180. These two don't add up to 0. Do they need to add to 0? Yeah, they do, right? They do. Yeah, they're supposed to. Am I right in thinking that... Did I get a negative wrong somewhere? Oh, wait. Oh, wait. Right here, these constants, I didn't add those constants correctly. I wrote 144, but I forgot to add 42 to that. Yeah, okay. That would definitely cause an issue. That would definitely break it. Okay. Okay. Hopefully. All right, so using the rational roots theorem, I was able to quickly get to a point where I was like, I think I made a mistake somewhere. So this is actually negative 102. And then when I distribute that negative, we have minus 186. So negative 102 minus... Oh no, this would be positive 102 after I distribute the outside negative. So now we have negative 84, right? Negative 84. Yep, negative 84. Okay, so let's try all this again. Rational roots theorem says that our options are plus and minus a divisor of 84 and a divisor of negative 1, where A divides the last term and B divides the first term, negative 1. So 84 has a bunch of factors. So our contenders are plus and minus 2, plus and minus 4, plus and minus 3, plus and minus 7, plus and minus 14, plus and minus 28, plus and minus 21, plus and minus, I think, 42, and plus and minus 84. I really don't think we're going to have to check too many of those, because if we have a larger number, like a huge number like 84, well, 84 cubed is going to be so much bigger than all these other terms that are like 80, 84 squared, etc. Right? So let's just hope that 2 works. But we still have the reasoning that if it's a positive root, then all of these terms would be negative numbers. No, I don't really know stats that well. You can ask, and I can try, but I'm not a stats guy, if I'm going to be honest with you. But you can try to ask. Yeah, of course. Oh wait, didn't we try 84? Oh, negative 2. The first terms would all be the same, right? Unless I messed up something here. Negative 55 minus 38 is negative 93. I got that correct. Oh, wait. What the hell am I doing? Okay. Negative 14 minus 38. Oh, no. There's no lambda squared in this second. There's no lambda squared in that second term. Okay. So I think that this is the correct characteristic equation. So we drop, or just add 0, essentially, to this first one. To negative 12, 24. Yeah, this didn't work, did it? Negative 69. This didn't work. Sorry, baby. Three, negative 11, 33, negative 60, 180, negative 3 didn't work. Man, I feel like I made an error earlier in the problem, but I mean, it's not enough yet to say for sure that I did. Yeah, this one doesn't work either. All these other numbers are just going to keep getting worse, I think. Unless I'm like, my intuition is just super off, but I think that all these other numbers are getting worse. Yep. I think I made an oopsie somewhere in the determinant calculation, because this is just super ugly. All right, let's take another crack at this thing. And this time around, I am going to try to do the simplifications that I was considering. Let's try to consider what I was thinking. So I can factor out a constant out of the determinant. And let's try this. 2 minus lambda over 2, 1, negative 1. Negative 2, 16, negative 1 minus lambda, 8, 2, negative 7 minus lambda. Man, I just don't know if this is going to make my life easier or harder. Like, I don't really love working with, like, fractional lambdas and stuff, but hey, maybe it does make life easier. I don't know. Let's add the third column to the second column. so that I get a 0 here. And then I have 1 minus lambda, so 2 minus 1 is positive 1. And then this one is a 1 minus lambda as well. Okay. Now at least I have a column of zeros or something. And now I can add... No, I don't that doesn't help. The thing I had in mind. -1, 2, -7 minus lambda. -2, 16. So what else can I do? I can... well, I like the idea of subtracting one of those rows from the other to... because we have that common 1 minus lambda term, right? So this would be 3 times the determinant of... let's take the third row minus the second row. So 16 plus 2 is 18. 1 minus lambda minus 1 minus lambda is 0. Sorry, baby. -7 minus lambda minus 2 is -9 minus lambda. Anything else that would make our lives easier? I mean, I do see the... I see the, freaking, cofactor expansion along the second column. I guess we want to do that. But I keep getting this wrong, so I'm going to explicitly swap the first and second columns. I'm kind of a dummy, but I just want to really make sure I don't make the mistake that I did recently. So now this is going to be -3 times -1 minus lambda times the determinant of the minor matrix 2 minus lambda over 2 -1 18 -9 minus lambda. Okay, so this is 3 times 1 minus lambda times when I factored out a 3, here's another typo. Look at that. When I factored out a 3, this should have been lambda divided by 3, not lambda divided by 2. Meow. I know. Yeah, I don't think that really made our lives any easier, if I'm going to be perfectly honest with you all. Oops. Yeah, I don't know if that really made our lives any easier. So let's distribute through that 3 again. And then we get, so -1 should have worked. Did I? Oh, son of a... Okay, I was jumping directly to -2 in this synthetic division, but I should have tried -1 first. Why did I forget? Of course, plus and minus, like 1 divides the last coefficient as well. Okay. Either way, we should get, now I'm kind of curious if I still had a typo or not here. So now we have -80. What? Okay, now I'm confident that there was a typo. There was also a typo somewhere. Damn it! Oh, they'll learn. Alright, well, anyways. We found 1 minus lambda should be a term. Oh, wait. That would mean +1 should be a factor. Which means that my characteristic polynomial somewhere was broken along the way. Because +1... What the hell is going... Okay, yeah. Calculating this characteristic polynomial, +1 should not be a root of this, because all of those terms would be negative. So I definitely made a mistake somewhere in this ugly calculation. And doing it in the more clever way really is turning out to be worth it. So multiplying the first row by 3, we get 6 minus lambda minus 3, 18, -9 minus lambda. So this is 1 minus lambda time... Oh, wait, no, it's not enough to say that this 1 minus lambda is a factor. It wasn't enough to just see that it's here to say that it's a factor. So, yeah, some issues popping up here and there. We've got lambda plus 9 times lambda minus 6 plus, what is this? 54? Is that right? 18, 36, 54. Yeah, plus 54. One minus lambda times lambda squared plus 3 lambda minus 54. Okay, well, let's frickin' go. Let's go. Plus 54. Oh, man. And then this splits as 1 minus lambda times here, let's I see a negative. So these two cancel out to 0. And then this factors as lambda times lambda plus 3. And then I'm doing some rearranging, and I get negative lambda times lambda minus 1 times lambda plus 3. Boom! There it is. I'm just going to confirm this, because I'm jumping ahead one step, and it's easy to make a mistake. This is negative. The first term is lambda minus 1 And then we have lambda times lambda plus 3. Meow. Sorry, baby. Okay, I got it. Yeah, I got that. Just want to make sure I don't make another little typo. You know, mental math, mathematicians make mental math problems, mistakes all the time. It's true. It really is true. So therefore, we have 3 eigenvalue eigenvector pairs. Lambda 1, oops, what am I doing? Lambda 1, let's order them. Lambda 1 is -3. Lambda 2 is 0. And lambda 3 is +1. Excuse me. Excuse me. Let's let in the loon. Kitty cat. Kitty cat. Okay. You're out on bail, baby. You gotta behave. Got to behave. Okay. So, lambda 1 is -3. What was our original matrix again? What the hell are we doing here? Well, our original matrix didn't have these minus lambdas, but we are solving. Reminder that we're solving A V1 equals -3 V1. So we can solve this system of equations. So lambda is -3. So this is 9. -1 minus -3 is 3 minus 1 is 2. And -7 plus 3 is -4. Okay, this simplifies. Are these? Okay, wait. These are kind of these are a little weird, but I see. I'm gonna put the second row, swap the first and second rows, and then divide that second row by -2. So 1, -1, -1, 0. The first row, let's divide everything by 3. So we get 3, 1, -1, and 0. And then this last row, let's divide everything by 4. 4, 2, -1, 0. We can row reduce this. And we do our Gaussian, Gauss-Jordan elimination, Gauss-Jordan reduction to solve this system of equations. So, second row minus 3 times the first. So it would be 3 plus 1 is 4. Minus 3 minus 1 is -4. 4 minus 4 is 0. 2 plus 4 is 6. -1 plus 4 is 3. 0. This looks like a problem to me. Because, hey, what's up? JXZ3YN, how are you, dude? How are you? You're not the J that I know, but that's okay. Good morning, dude. I'm making mistakes left and right over here today. I think I finally found the eigenvalues. It would be a remarkable mystery if I made an error in this determinant and it still splits correctly. So I feel like I made an error somewhere. I feel like I made an error. Because this matrix is not degenerate, and that's an issue here. We want something degenerate. 3, -2. So 2. Yeah, 2 minus -3 should be 5. See, I knew that there was an issue somewhere. Okay, so 2 or -1. What? Wait. -1 minus. Okay. I'm writing the system of equations a plus 3. Oh, wait, yeah. A plus 3i times v equals 0. So this matrix A, if I add 3 times the identity to it, it's get like super explicit because I'm like making mistakes today. 6, 3, -3, -2, -1 plus 3. No, so I got this part fine. 16, 8, -7 plus 3 is -4. Okay, so I think I wrote... Oh, geez, I erased some parts. I think... Yeah. -3. I wrote 6, but I really meant 6 plus 3 is 9. Right? Yeah, that's what I meant there. See, I'm making a lot of mistakes today. This is why mathematicians, when they're doing a problem on the board, they're never working it live for the first time, because it's easy to make mistakes for anybody, y'all. I'm telling you. Math is full of mistakes, and you just gotta know when you can catch. See you, sir. Exams on head. Hey, thanks for sticking around this long, Sudip. It's nice to meet you, man. I'm glad that you enjoyed it, dude. Thanks for sticking around. Dude, okay, so we've been making some mistakes today, and that's human. Oh, son of a... See, okay. When I wrote... Oh, no, it's fine. 9, 3, -3, -2, 2, 2, 16, 8, -4. Those are fine. Let's try this again. And work more carefully. So the first row, divide by 3. Second row, divide by -2. Last row, divide by 4. 4 to -1, right? Now, interchange the first and second rows. First row is the same. Second row is row 2 prime is row 2 minus 3 row 1. And row 3 prime is going to be row 3 minus 4 row 1. Okay, so row 3 minus 3 is 0. 1 plus 3 is 4. -1 plus 3 is 2. 0 plus minus 0 is 0. 4 minus 4 is 0. 2 plus 4 is 6. -1 plus 4. Yeah, -1 plus 4 is 3. Okay, now we fixed it. I don't know where. Now these two, rows 2 and 3, are dependent. 1, -1, -1, 0, 0, 2, 1, 0. And I can see if I triple that second row, it equals the third row. So the third row is dependent on the second. Finally, okay, now this corresponds to the system of equations x minus y minus z equals 0 and 2y plus z equals 0. Take z equal 1. Then y is -1/2, and x plus 1/2 minus 1 equals 0. X equals 1/2. So our solution, x, y, z, which is vector 1, is any scaling of 1/2, -1/2, 1. So, and this is equivalent to 1, -1, 2. So I'm going to take eigenvector 1 is 1, -1, 2. Just to have some level of confidence that all of these hand calculations did not go wrong, and that these are eigenvector, eigenvalue pairs. Let's confirm. What is A times V1? 1, -1, 2. So we've got 9 minus 3 is 6. 6 plus 6. No. 9 minus 3 is 6. 6 minus 6 is 0. Oh. Yes. This, what I'm actually calculating right now is a plus 3I, and it should be equal to 0. I wanted to go back to the definition of eigenvalue, eigenvectors. So forget about this one. Our original matrix was this, and we want to see that A times our eigenvector that we found, 1, negative 1, 2, 1, negative 1, 2, should be equal to negative 3 times V1. That's what, we think that this should be true. We found some vectors that, or a vector that should satisfy this. So I don't want to assume that we're doing a plus 3I anymore. Okay, now we've got 6 minus 3 is 3. 3 minus 6 is negative 3. Cool, we're on the right track. Negative 2 plus 1 is negative 1. Negative 1 and 4 is 3. And then 16 minus 8, 8, 8. 8 minus 14. 8 minus 14 is negative 6. Sick. So, voila. AV1 equals negative 3V1. So, I think that I'm finally on the right track on this. And that was just the first eigenvalue, but the rest maybe should be easier. Maybe. Let's make sure that we don't make this typo again. So this was the resulting matrix for eigenvalue 1. Now eigenvalue 2 we found was 0. So then, well, a minus 0I is just a. So we want to solve the system of equations 6, 3, negative 3, negative 2, negative 1, 2, 16, 8, negative 7, times a vector equals 0. 2, 1, negative 1, 0. Negative 2. Now if I add row 2 equals row 1, row 2 plus row 1 prime, then negative 2 plus 2 is 0. Negative 1 plus 1 is 0. 2 plus negative 1 is 1. We get a 0 there. Is that? That feels a little funny. But maybe that's okay. Maybe that's okay. Okay, well, let's find out. Now, third row minus 2 times the minus 8 times row 1 prime. 16 minus 16 is 0. 8 minus 8 is 0. Ooh, wait, do we get 2 unknowns? Negative 7 plus 8 is 0, is negative 7 plus 8 is 1. Is this, can we get, oh my gosh, does this work? Hey, Squared Time, how are you, man? How are you? Welcome to my practice stream. Oh, yeah, okay, yeah. So then this corresponds to equations of the form 2x plus y minus z equals 0, z equals 0, and z equals 0. Okay, yeah, no. This is going to work. So then, well, this just boils down to the system of equations. 2x plus y equals 0. Now we can take maybe x equals 1. Then our solution vector, well, I took x equals 1, y equals negative 2, z equals 0. Yeah. That makes sense. So it's just pointing in like a vertical direction. Or not in a vertical direction. It's on the xy plane with 0 component. Okay, yeah. So eigenvector 2 is 1, negative 2, 0. I feel confident now that I'm not going to double check it on this one. This is for the second eigenvalue. And for the third eigenvalue, I think it was positive 1. Yeah, positive 1. We recall A is this, so then therefore A might, and we're solving A V3 equals V3. So we subtract so A minus the identity matrix, so like subtract lambda across the diagonal, 6 minus 1 is 5, negative 1 minus 1 is negative 2, negative 7 minus 1 is negative 8. And we solve the system of equations. Oops. We solve for the system of equations, setting this to 0. Well, I can already see that the third row is dependent on the second row. Oh, wait, no. That's not true. Negative 2, negative 2, 2. That's not true. But the second row looks easy to work with. 1, 1, negative 1, 0. The first row looks like the trickiest one to work with. And then the third row from the left-hand side is not too bad. It simplifies like that. 2 minus 2, 1 minus 2, negative 1 plus 2, 5 minus 5, 3 minus 5, negative 3 plus 5. And now the second and third rows are dependent. Cool. So I added the second row to the first row, and then therefore x equals 0. I don't really need to write this xyz part. Well, no. Let's do it. xyz where x equals 0, y minus z equals 0. So I'm going to take v3 equal x is 0, y equals z. So take z equals 1, then y is 1, and v3, our third eigenvector is 0, 1, 1. Yo, hi, what are you doing? Are you doing like lines and planes? Kind of, yeah. Yeah, what we do here is make a inverse. I'm studying the same topic now in high school. Heck yeah, yeah. I'm studying some similar stuff. This, like, calculating the inverse of a matrix is sort of like the beginning, or like it's a previous section. That's like chapter 2 of this book. I'm in chapter 5 right now, which is about finding eigenvalues and eigenvectors of a matrix. So a matrix tends to have special vectors such that A times V equals lambda V. And have you learned about the determinant yet? The determinant of a matrix? Because if you have an equation like this, then AV minus lambda V equals 0. I can subtract the scaling multiple. Well, first off, what does an equation like that mean? There are some special vectors such that when we multiply by a matrix, it's just a scaling. It's a scalar multiple of that matrix. Typically, there are, at least in the plane, there are 2. They don't have to be positive and negative, but I just want to point out that it can be negative. I'm just making up the solutions. But yeah, notice that both of those eigenvectors lie on the same line. So it has the same angle. The matrix didn't rotate the vector at all. It just scaled it like further. You work with planes. You just started studying vectors with matrices. Hell yeah, man. So that I'm studying like the college level class. Usually it's college. I mean, maybe your high school is awesome. Mine was not awesome. But usually this is a college level class. Taking what you're studying, like learning what you're studying, and continuing a whole subject of math called linear algebra. And bro, it's so sick. Like, yo, yeah, you studied interceptions and normal vectors. Yeah, dude. Normal vectors, we introduced that in chapter 1 of this book, and we introduce it with the formula that two vectors are normal or orthogonal if the dot product of those two vectors is 0. Why is this true? Well, we can see it from this formula that you can prove. So if theta is pi over 2 or 3 pi over 2, then the two are orthogonal, right? Like they create a right angle. And cosine theta is 0. So u dot v equals stuff times 0, and that's 0, right? Yes, I have it right here in my notebook, man. That's so sick. Isn't it cool? Dude, I love this field. This field of math is like my favorite field of math, actually. It's very cool because it gets abstract. It gets super abstract, actually. Like, so I'm in chapter 5 right now. Last time we were studying some cool stuff about volumes in like higher dimensions. Like if you have like a lower dimension in a higher dimension, how do you find the volume of that, of n boxes? Recently, you probably haven't learned about the idea of a vector space yet. In chapter 3, section 5, I was studying inner products, which is an abstraction of the dot product. I just mentioned the dot product of two vectors. We can abstract that to a more general idea called an inner product. As long as you have these properties, well, that's a mess, but there are 4 properties of the dot product that turn out to be important. And you can find other places in math where other structures, other objects that behave the same. They have the same 4 properties. And then it's an abstraction. Here's some stuff about calculus and applying linear algebra about lines and planes to calculus, which is super sick because the integral turns out to actually behave very similarly to linear transformations. The integral actually behaves similar to a matrix. So here was like a problem that I worked recently from chapter 3 about the integral, coordinatization of finite dimensional vector spaces. Here's some theorems and algorithms and stuff. Yeah, this is a whole field of subject. Like if you're just learning matrices, dude, like, and you find matrices cool, this is the stream for you, man. I'm practicing every day. Linear algebra is the most useful math that there is, but it's also the beginning of abstract math and abstract concepts like vector spaces. So I love it. I think it's the greatest math. But yeah, so you found this is in your notebook right now. Hell yeah, dude. Okay, so this problem, diagonalization. Find the eigenvalues and corresponding eigenvectors vi. So I found the eigenvalues, then I found the eigenvectors. Now we have to find an invertible C and a diagonal D such that D equals C inverse AC. Okay, so we are very close to this, to finalizing this. I'm just going to repeat that we have 3 eigenvalue eigenvector pairs. Lambda 1 is -3. Lambda 1 v1 is -3 comma the vector 1 -1 2. Yoink. Over here we have, I found lambda 2 and eigenvector 2 is 0. Lambda 2 was 0, and eigenvector 2 is 1, -2, 0. Cool. And then the final eigenvalue-eigenvector pair we found was, let's move this out of the way. And the final eigenvalue-eigenvector pair was lambda 3 v3 equal to 1, eigenvalue 1, and eigenvector 0, 1, 1. So, and we want a diagonal matrix D and invertible C such that D is equal to C inverse times our original matrix times C. We have a theorem that D is the matrix with eigenvalues in the diagonal, which is, we found lambda 1 is -3, lambda 2 is 0, and lambda 3 is 1. I didn't know that eigenvalues can be 0. I mean, that's kind of cool. I didn't realize that. Maybe I should have realized that. I don't know. Maybe I should have. And C is going to be the corresponding eigenvectors. Which are 1, -1, 2, 1, -1, 2, 1, -2, 0, 1, -2, 0, and 0, 1, 1. 0, 1, 1. Cool. I can see, well, I can't immediately see that C is invertible, but dude, I believe it. I think it is true that that is invertible. So if I want to check this equation, and I multiply by C on both sides, or on, yeah, multiply by C on the left of this equation, then CD should equal AC. This is what I want to check, this, just to double check. I mean, we have a theorem that if everything went right, these are our solutions to that equation. But now I just want to double check. So what is CD? CD is 1, -1, 2, 1, -2, 0, 0, 1, 1, multiplied by our diagonal matrix, -3, 0, 0, 0, 0, 0, 0, 0, 1. So I don't need to do the whole, let's see. No, I'm going to make sure I don't say something wrong here. But I think that multiplying by this matrix means multiplying the first row by -3, multiplying the second row by 0, and multiplying and keeping the third row, preserving the third row. I'm pretty sure that that's right. I think that that's right. Yeah. That's how I can see the action of that matrix. And now, what is A times C? A, we found, A is our original matrix that we're building all of this from. Our original matrix is this. Dude, you should tell all your friends. You should tell all your friends about this stream in your class. You know? Because streams are so much more fun when you have when you know people in the chat and you're like chatting and solving like, dude, you could like work on your homework problems together here, and like use this as like a study group for your class, right? I remember we were in a voice call with my friend doing some problems and we didn't want to see the solutions, and it was even hard with our notes. But when we found the solution, man, we were so happy. I can't. Yeah, man, I'm telling you. Can you please go fast over the problem and in a few words, what are eigenvalues? Let me copy that to my notebook for fun. Dude, I don't take all requests, but I will absolutely take that request. Dude, so multiplying a vector by a matrix in general, multiplying a vector by a matrix will take your vector to some other vector, right? Usually, like it could rotate it, and then it could scale it, it could stretch it, it could do something like that. An eigenvector, eigenvectors are special vectors that exist such that when you multiply that special vector times the matrix, it stretches it. Notice that this is just a scaling. It stretches or shrinks that vector, and maybe it rotates, and maybe it like flips it along, like reverses the direction is what I'm trying to say. So if this is our original vector v, and maybe I say that this is v1, because there can be two different, like in the plane, there are probably two eigenvectors. Oops. Usually there's two eigenvectors in the plane, but not always. So I'm drawing the line, like the dotted line is all of the multiples of vector 1 and vector 2. Like, you can multiply vector 1 times any number and you'll get some point on that line. For any point on that line, you can multiply v1 by a number to equal that other vector. So, since a vi equals lambda I vi, this is a scaling of vector 1. Maybe, I'm going to try to make sure that both of those vectors are on this line, right? So maybe AV1 is, maybe that's like 3 times V1. This is something like around 3 V1. Oops. Like I tripled that vector, or 2.5 times that vector, something like that, right? And maybe this one over here, vector 2 is a special vector such that AV2 is maybe like negative 1/2 times V2. Does that make sense? Like, so it stays in the vector keeps the same angle that it had. It's still in the same subspace spanned by that vector, but the matrix A will stretch it. It might flip the direction. this is just an example. I'm making this up. Like it doesn't have to be. V2 could also be a stretching of V2. Maybe this is a V2. I'm just making up this example right now. But it keeps, my point is that whatever A does to V2, it stays on this same line. It stays on the same line as it originally was, including like a negative. Like V1 was stretched in the same direction. V2 was flipped and shrunk a little bit. Right? So it's a scaling. And, well, if there are solutions to that equation, if we do have a solution to this equation, then you can subtract that vector from both sides, that's stretched, that scaled vector from both sides, and then you can factor out vi from both sides, and we'd have these equations. So A minus lambda I is the identity matrix. Then this means you'll learn about something called the determinant. And we can take the determinant of both sides and set that equal to 0. So the determinant should be 0 because the determinant, let's see, how do I say this? Why would this be true? Well, determinant of AB of two matrices, the product of matrices, is the determinant of A times the determinant of B. So in particular, if B is, one column is a column vector, then the determinant of AV equals determinant of A. Well, V is not a square, so it doesn't make sense to talk about the determinant of a vector. My bad. So that's not the proof of this, but how do I prove that? This line here. It intuitively seems true, but my intuition, I'm having a hard time saying exactly why. Oh, you've learned determinants. Dude, your high school is much better than mine was. So if you multiply a vector by a matrix, you can find a value that if you multiply the vector by it is the same as matrix. Yeah, exactly. So, yes. So we can find special values called eigenvalues that will then find us the vector that it corresponds to by solving determinant of A minus lambda I. And we want to set that equal to 0. So since you've learned determinants, here is the determinant of that matrix minus lambda I. So you subtract lambda across the diagonal because, well, lambda I is lambda across the diagonal and zeros everywhere else, right? This is lambda I. So if you subtract that from A, then we get this, and we calculate the determinant. I tried to do it with the diagonal approach, and I totally messed it up. I made some typo somewhere. So then I tried again, and I used a more clever argument, simplifying the determinant, and eventually I found After calculating the determinant of this thing, I found this equation. And remember, we set this equal to 0. So this is called a characteristic polynomial. That's an important thing to know. This is the characteristic polynomial of the matrix A. And it is the way that we find these special values, these special eigenvalues. So I found eigenvalue 1 is -3, eigenvalue 2 is 0, eigenvalue 3 is +1. Then I solved the eigenvalue equations for each of them, and just do our normal solving systems of linear equations that we've learned in previous chapters, and you're probably learning right now in your class. So I solved this system of equations. I found that for the first eigenvalue pair, it corresponds to this system of equations, which has one free variable. It has one free variable, so I can choose a value for it. I chose z is 1, then y is -1/2, and then x is +1/2, which would be this vector. I just doubled it because you can pick anything along that line. And so this is my first eigenvector. I double-checked here by multiplying. I took my original matrix A just to double-check and make sure A times VI, when I multiplied these two, indeed, this is -3 V1. I said VI, I meant V1. So that's kind of magical, man. I think that's really cool. We found a special vector that gets stretched. So for eigenvalues, if you get, for example, x plus y equal 1, then you can take a value for y or for x. Yes. I'm tempted to make up an eigenvector problem, but it might end up being messy. Dude, you're getting me on a tangent, and that's a good thing. If it's okay with you, it's okay with me. Anytime I can in math, I like to work with the numbers 1, 2, 3, and 4. I'm going to make up my own problem, man. Let's try to find the eigenvalues for this matrix. 1, 2, 3, and 4. Well, first off, will it have eigenvalues? I think it should. It is a invertible matrix. It's an invertible matrix because the second row is not a multiple of the first row, right? Oh, you're doing it with me. Pause the video, man. No joke. Pause the video and try it. And when you need a hint, unpause the video. It's okay. I don't mind if you're not in real time chatting. So then, okay. So here's how it goes. We want to solve this equation. That means AV minus lambda I equals 0. That means determinant of A. Let's write this here. Therefore, determinant of A minus lambda I is going to equal 0. That means 1 minus lambda, 2, 3, 4 minus lambda. We might get really ugly solutions to this polynomial, but we have the quadratic equation, so we can find it. This is going to be lambda minus 1 times lambda minus 4 minus 6. And this is, I said lambda minus 4, but I wrote 4 minus lambda. Lambda minus 4. this is lambda squared minus 5 lambda plus 4 minus 6. Well, plus 4 minus 6 is negative 2. Okay, and as I said, this does not, I don't think that this has rational roots. And that's okay. We can use the quadratic equation. Lambda equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which is going to be 5 plus or minus the square root of, what is that, 33? Okay. Then, so let's take lambda 1 equal negative 5 minus root 33 over 2. And lambda 2 is going to be 5 plus root 33 over 2. My iPad is about to run out of battery, so let's plug it in. No, I'm gonna write it with you. Okay, yeah, take notes like while I'm working it, right? Yeah, take notes with me, man. Like seriously. So, do you see how I got to this point? Are you with me so far? Let me know if you want me to explain anything further. On this, I'm using the determinant of a 2 by 2 is a determinant of a 2 by 2. Dang it. A, B, C, D is AD minus BC. I kind of already assumed that you know that. So far it's easy. Yeah, hell yeah, dude. And we set that polynomial, that quadratic, to 0. I use the quadratic equation, and now we're here. So now I'm going to be solving a minus lambda 1 times vector 1 equals 0. So here, this might get a little ugly, but we can try it just to see what happens. 1 minus lambda 1, 5 minus root 33 over 2, 2. And then we have 3, 4 minus 5 minus root 33 over 2. I wish that this was like a nicer thing, but that's okay. All right, so we have this system of equations. So that first term, I see it as 2 halves minus all that stuff. So we have negative 3 halves, right? Plus 33, plus root 33, to 0. 3, and then 8 halves. So 8 halves minus 5 halves is 3 halves. And again, plus root 33. Times 0. Solving this system of equations, we can double both lines. Oops. Have to double that. Right? And now we could Well, I'm tempted to divide by 3, but I don't think we should. So multiply by the complex conjugate. 6 times 3 minus root 33. And I want to see that these two lines are dependent, because they should be. 3 minus 33 is negative 30. Oh, wait. Sorry. No, I got that wrong. What I'm calculating is 3 plus root 33 times 3 minus root 33, which should be 9 minus 33, right? Which is negative 24. And I want to keep the first entry the same, so let's keep it like that. Solving this system, well, 18 minus 6 root 33 minus 24, or even better, before distributing, let's divide the whole second line by 6. Then we have 3 minus root 33. 3 minus root 33 and negative 4, 0. And voila, now these two lines are clearly dependent. So this is equivalent to the system of equations negative 3 plus root 33 times x plus 4y equals 0. The second line is equivalent to the first. Yeah, so far it's easy. Negative root 33. Yeah, we did choose the minus value for lambda 1. But remember that we subtracted lambda 1. So I think that what you're thinking of is I distributed that negative, so it should be plus root 33 here. Yeah. That's where it happened. Yeah. Okay. So now, what's the cleanest way to show this? I'm going to take, I think x equals 1 is going to be the nicest. Then y equals 3 minus root 33 divided by 4, right? If x is 1, yeah, if x is 1, then y is that. So an eigenvector can be 3 minus root 33 over 4, or we could quadruple the whole thing and then we get something slightly nicer. Yo, dude, look at that. That's crazy. Isn't that crazy? So we found that as the first eigenvector. You can try this with the second eigenvector yourself, or you can find the second eigenvector by doing the same exact solving a system of linear equations using this eigenvalue. So try this for yourself to find the second eigenvector. What I'm going to do is I'm going to show let's double check. A times V1 should be equal to, what was it again? 5 minus root 33 over 2. 5 minus root 33 over 2 times V1. Is this true? Should be. I made up this problem for myself. And what's cool is that because I made it up for myself, I usually make up problems with 1, 2, 3, 4. And just see what happens. 1, 2, 3, 4. We got something complicated, but yo, let's see if it works. 4 and 3 minus root 33. We have 4 plus 6 minus 2 root 33. Right? Which is 10 minus 2 root 33. Now in the second, we have 12 plus 12 minus 4 root 33, which is 24 minus 4 root 33. Okay. So we found something gnarly. That's a crazy, interesting vector. So here I calculated a times v1, and instead of trying to like factor that or something weird, instead I'm going to calculate the right-hand side. 5 minus root 33 over 2 times our eigenvector 4, 3 minus root 33. So here I'm calculating lambda times v. We found lambda and we found v. So we multiply. 4 divided by 2 is 2. 2 times 5 is 10. 2 times negative root 33 is negative 2 root 33. And now, wait. Shoot, what's going on with the second entry? Was it a 4 minus? No, it's 3 minus root 33. What's going on with the second entry? Maybe this is expected. Let's see what happens. 15... Let's keep everything divided by 2. Then we have... oh, yeah. Okay, so 5 minus root 33 times 3 minus root 33 is 15 plus minus 8 root 33 plus 33. 33 plus 15 is 48. Dude, I have no idea what's going to happen in this, but I think we got it, dude. I think we got it. 48 minus 8 root 33. And we have 10 minus 2 root 33. 48 divided by 2 is 24. 8 divided by 2 is 4. Does that? I think it does. Yo, let's fucking go. Do it. Look at that. Let's go. They matched. I'm very happy about that because I made up this problem and it turned out to be ugly numbers sort of, but it worked, right? OMG, isn't that cool? Isn't that super cool, dude? Like, I'm actually just like, heck yeah. This is my tip to you. When you learn math, try to find a way to use the numbers 1, 2, 3, and 4 and just see what happens. See if you can come up with an example for yourself of that uses 1, 2, 3, 4, right? Dude, seriously. I wish somebody told me that tip. Like, today, definition of a determinant of the second order. Somebody tells me, here's the second order determinant. A, B, C, D is A, D minus B, C. My mind, I'm immediately going to go like, oh wait, determinant, we want to use vertical bars. For me, nowadays, I'm going to go, okay, cool. What's the determinant of 1, 2, 3, 4? 4 minus 6. The determinant of 1, 2, 3, 4 is negative 2. I'm going to make up my own examples. I'm going to try to make up my own shit and try to figure out what happens. Anytime somebody tells me, like, dude, addition? Okay. 1 plus 2 is 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10. Of course, there's really cool properties about these triangle numbers, but I'm not going to get into that right now. I just want to come up with examples for myself. Anytime that somebody teaches me something nowadays, I'm going to be like, what happens if I try it with 1, 2, 3, 4 and see what happens? Does this theorem work? And it did. It did. I just made that up. Heck yeah. Okay. Wait, what the heck? Oh, no. My iPad was plugged in, but the cable wasn't plugged in. I used the wrong cable. Whoops. I plugged into the wrong cable, but anyways, dude, how are you? Thank you for hanging out with me. You're probably the only person who's ever going to watch this video this far. Dude, in the background this whole time, that's been me. I'm a guitarist. While my iPad recharges, can I play you a quick little guitar song, dude? I'm a guitarist and a mathematician, and they're both my hobbies, and I'm very proud of them because I think that they're pretty awesome hobbies. Let me play you a very simple, nice little tune called Lagrima. No, you know what? I want to play Bach. I'm going to play Bach for you, man. hope you enjoyed it. Thank you, man. Thank you, bro. That is fucking fabulous. Thanks, dude. Thank you. I appreciate that very much. Yeah, so this is actually my second channel. I have a channel dedicated just to classical guitar. That's why there's all these names on the guitar. They're all my channel members. They're like my kind of like Patreon supporters. So, dude, if I'm not streaming here, I'm probably streaming there. It's a much bigger community, actually. So, thank you. It's nice to meet you. Okay, how long is it? We've been almost 3 hours just practicing math and doing this problem. Oh my god! All right, let's wrap it up, John. Wrap it up. Hell yeah, dude. Yeah, would love to see you there sometime. We got a pretty cool community over there, like a lot of people who are into math and guitar, and so I use my guitar as music, as background music here, and then I use my math that I'm drawing and writing here as my background visual content for the for the guitar stream. Right? Like on the guitar stream, I'm just practicing. I'm practicing and doing scales or working on music and trying to get better at my guitar songs. But on the side, I have my math that I'm doing on the other channel. And yeah, I think it's kind of a cool idea. It gives like a little bit of dopamine, a little bit of stimulation, you know. All right, let's go. Let's keep going. All right, I want to wrap up this problem. And believe it or not, I might even want to do another thing from the next section. I usually shoot for like 1 or 2 hour streams, but this one's at 3 hours. That's crazy. That's crazy. Okay, so so I showed you asked about explaining eigenvalues and eigenvectors. That's a cool thing. Now, one thing that's amazing about eigenvalues and eigenvectors is that that we will get this equation. This equation is incredible because it makes it quite nice, actually, to calculate large powers of a matrix. A to the k would be CD C inverse raised to the k. Do you see? Yeah, you see my iPad again, right? This is a telescoping product. Think of it. We have CD C inverse times CD C inverse times ... CD C inverse. K times. Well, if I rearrange, the C inverse and C's all cancel out, except for one on the left. We get D to the K and C inverse. So, this gives us a way to calculate A to the K, a large power of a matrix. A to the K equals C D to the K C inverse. And because D is diagonal, meaning lambda 1, lambda 2, lambda n, well, dude, D to the K and zeros everywhere else. D to the K is easy to calculate. It's lambda 1 to the K, lambda 2 to the K along the diagonal. You follow? You with me? So, A raised to the K is just a product of these three matrices, which are relatively easy to calculate. So eigenvalues and eigenvectors, by finding the eigenvalues, it can make large powers of matrix multiplication easy. So let's wrap it up. The theorem says that D is the matrix with eigenvalues in the diagonal, and C is a matrix with eigenvectors as the columns. And if this is true, then this is true. This is what I want to calculate, just so I can avoid also calculating C inverse. But we could do that. I don't know. It's just tedious. C is 1, -1, 2, 1, -2, 0, 0, 1, 1. Okay. Let's do this matrix calculation and do the 2 match. Let's see. 6, 3, -3. 6, 0, 0. 0, 3, 0. -2, -1. Wait, what? -2. -1. Oh. Okay. No. What the hell? What the hell? Where's our matrix A? I'm pretty sure I copied there. Pretty sure I copied that. Yeah, yeah, that looks like the same matrix. All right, so we have, I'm blanking right now. Oh, I know. Yeah. So, dot product of second row and first column, -2 plus 1 is -1. -1 plus 2 is 3. Oh! What the F? What the F? Okay. Well, I'm getting 3 here, and it shouldn't be. -2 plus 2 is 0. Why am I blanking here? Did I copy C wrong? No. Did I do this multiplication wrong? Yes, I did do that multiplication wrong. That's the problem. This is the problem. Okay. Second row dot product first column is +3. Yeah, that's the problem. Okay. Oops. I knew something was wrong. Let's double check the rest of that row. Yeah. Second row, second column is 0. Second row, third column is +1. So I don't know what I was doing there. I don't know what happened. Let's double check the third row. Third row, first column is -6. Yeah, I don't know what was going on here. -6. 0 and 1. First row, -3, 0, 0. -3, yeah, -3, 0, and 0. Yeah, this should be a 0. So I did I was just moving too fast. I don't know. Oh well. All right, now the first row matches correctly. The second row here, -2 plus 2 is 1. 1 plus 0 is 1. Negative 2. Negative 2 plus 2. The red lines are screwing me up. Okay. Second row, second column. Negative 2 plus 2 is 0. And then 0. So this is a 0. That's correct. Negative 1 plus 2 is positive 1. So those numbers are matching again. 16 minus 8 is 8. 8 minus 14 is negative 6. Yep. 16 plus 16 plus 0 is 0. And 0, 8, 8 minus 7 is 1. Boom. Look at that. Verified. These two matrices match. So CD is equal to AC. And we finally got it. Okay. So, heck yeah. So I'm done now with that problem, finally. It took a while. It's not, this is why we give these problems to computers. This is why we buy GPUs, dude. GPUs are very good at this stuff. Humans are not good at this stuff. Humans make typos all the time. Okay. Last problem that I have for today is this one. I'm not going to work this problem, but I'm going to work the problem that it's related to. So there's an example about the Fibonacci sequence. It's another recursive sequence. This is a recursive sequence, 0, 1, and then the next number is always the average of the last two, the mean of the last two. Instead, I'm going to work that same problem for the Fibonacci numbers. And this time I want to see if I can get this correct the first time. So, part A. Find a matrix which represents the Fibonacci sequence. Have you seen this one yet? Squared time? Because based on the math that you know already, there's a matrix that captures the Fibonacci numbers. Okay, so what is the sequence of Fibonacci numbers? We want... We want to capture the numbers 0, 1, and then every term is going to be the sum of the last two terms. Okay? This is like my little shorthand to write that recursive definition. Then I could write Fn, for example, F0 and F1, I can write as a column vector of 0 and 1. How does this go? I'm trying to see how to, because I know the answer to this one, but how do we constructively build it? in general, we could write these as column vectors like this. Dude, I always mess this up. I think that this works out better. It matches the book's example, I think, if I write the next number first and then the second number, the current number second. I always get this wrong. So if I square that matrix, then I have 1 in this entry. I have 1 plus 1 in this entry. And then I have 0 plus 0 in this entry. And I have 0 plus 1 in this entry. F cubed would be 1101 times 1201, which is this never works. 2 plus 1 is 3. 0 plus 0. Yeah, this matrix represents Fn will be 1n 0 1 in general. 0. So this is not the right matrix. But right now, again, I'm guessing at it. I want to see how I can build, because the one I always find doesn't match the one that the book finds, which is driving me crazy. Because I've tried, you know what the Fibonacci sequence is just out of fun, no idea about Fibonacci matrices. Well then, dude, here you go. I'm trying to see if I can build it out of linear algebra, but I'm pretty sure that this one works. Does this one work? I think that this is the one that the book uses. So because I always want to use that first one, but it's not what the book uses. I think that the book uses this one, and then my numbers should match. So what is F? If I multiply that matrix by itself, I'll write it here. 1, 1, 1, 0. So 1 times 1 plus 1 times 1 is 2, right? And then in the upper right entry, we have 1. Bottom left entry, we have 1. And then bottom right entry, we have 1. Right? What is F cubed? Well, it's F. Let's write it out just so that you see it. F times F squared. So 1, 1, 1, 0 times 2, 1, 1, 1, which is 2 plus 1, 1 plus 1, 2 plus 0, 1 plus 0. Okay. Where are we going with this? These numbers are starting to look familiar as the first Fibonacci number, the second Fibonacci number, I think the second Fibonacci number, and the third Fibonacci number. And that pattern holds. That this is the fourth Fibonacci number, the third Fibonacci number, the third Fibonacci number, and the second Fibonacci number. Oh, and yeah. So you did this exercise. You've seen this. You've seen that this, heck yeah. So today you get to learn. You get to see this amazing math fact then. This is just the beginning. So we found a matrix F such that F to the n is Fn plus 1, Fn, Fn, and Fn minus 1. Okay? So, does F have eigenvalues? Why do I care about that? Let's pause. We don't care about that. What we care about is find a formula to approximate Fn for large n. So we want to find a, hey, what's up, theoretical physicist and polymath? Polymath? Did you miss the H? I am a computer scientist. I studied computer science, and I worked in Silicon Valley at Google and Apple and stuff like that. But now I want to practice math for fun, dude. I just want to learn math, and I want to get really, really good at math. I do want to teach math next, in the next chapter of my life, but I'll be teaching like high school math, not college math. I'm learning college math for fun because I love it. Yeah, you enjoyed linear algebra before quantum. Yeah, dude, for real. Linear is so useful in so many fields of science and math. Like, linear is like the most useful math that there is. So I'm practicing just because I want to get really good at linear algebra. So here's our goal. We want to find a formula to approximate Fn for large n. Well, then what we want to find is F to the n for large, capital matrix F for large n, right? Because we can take one of those entries to get an approximation. From the section that we were just learning was that if we use eigenvalues and eigenvectors, squared time, let me know if you're still there, dude, because I just showed squared time this for the first time. Are you still there? Are you still with me, man? Like, let me know if you're following me on this. We just learned by using eigenvalues and eigenvectors, we can get this equation. This is called diagonalization. And we get that from this equation, A equals, D, I think we write it as D equals, that's a C. D equals C inverse AC, you multiply both sides by c and then c inverse, and then you raise both sides to k, and then you get a telescoping product. And so you have a to the k equals c d to the k times c inverse. Fill in the details if you're interested. And as I said, these matrices are easy to work with, easy to calculate. If we find C and D, we can approximate or find or calculate a to the k. Well, we can approximate Fn via F capital F to the n. That's how I'm going to put it. So to find C and D, we calculate the eigenstuff I'm using capital F for this matrix. So I showed that this matrix captures the Fibonacci numbers. So we solve the determinant of F minus lambda I to find the characteristic equation, the characteristic polynomial, and we set that determinant to 0. So I have 1 minus lambda, 1, 1, and minus lambda. And this matches this, which is lambda squared minus lambda minus 1, and I set that equal to 0. This admits this yields eigenvalue 1 and eigenvalue 2 by using the quadratic equation. X equals negative b plus or minus, well, I'm going to, again, negative b plus or minus the square root of b squared minus 4ac. So b squared plus 4 is square root of 5, all over 2. So these are the eigenvalues of the Fibonacci matrix. These are the eigenvalues of the Fibonacci matrix. We find the corresponding eigenvectors v1 and v2 by solving the equation a minus lambda I v equals 0. So A, well, I keep using A, but I mean to use F for our Fibonacci matrix. So looking at our characteristic equation and plugging in lambda 1 into that thing, we have 1 minus root 5 over 2. 1 in the bottom left, 1 in the top right, negative lambda and we set this equal to the 0 vector, and we solve this system of equations. You have to go. Dude, bro, squared time. I'm telling you, dude. Later on, watch this VOD because, bro, exactly the same thing that we did. We made up this problem earlier, and we found these gnarly, like, interesting eigenvalues for the matrix 1, 2, 3, 4. We're going to do the same exact thing, but now for the Fibonacci matrix. And bro, you're going to enjoy this. I'm telling you, you're going to enjoy this. So watch the VOD later and leave a comment about it. And tell your teacher. Tell your teacher about it, dude. Because this, like, today you learned. You're one of today's lucky 10,000 people who learned this idea today. When did I start learning and teaching math? I studied a math degree like 15 years ago. But then I went into software. I've been studying math for fun, for myself, here and there, randomly. Yeah, I love math. I think it's a really nice field of study. Okay, so we know that this is going to correspond to this system of equations. Like, this does create a degenerate matrix system. So you can go through the calculation to see that those two rows are linearly dependent, but I'm going to, for sake of time, skip that right now. So then V1 is xy, where x plus -1 plus root 5 over 2 y equals 0, right? I'm going to take y equal 2, or no, let's take y equals 1. I think that this is how the book does it. Take y equals 1, then x equals 1 minus root 5 over 2. So eigenvector 1 is 1 minus root 5 over 2, comma 1. So there's our first eigenvector. Next, we're finding eigenvector 2 for eigenvalue 1 plus root 5 over 2. So we're finding eigenvector 2 for the second eigenvalue. A minus lambda 2I is equal to yeah, the mathematician part of me is like, no, this sentence is not correct. It's not the correct thing. If we're solving this linear equation, this system of equations corresponds to this augmented matrix and solving this augmented matrix. I'm going to make sure I get this right. 1 minus eigenvalue 2 is 1 minus root 5 over 2, right? 1, 1, and we have -1 minus root 5 over 2. All set to 0. And again, you can show it for yourself that, that these two lines are linearly dependent. Double one line, multiply by the complex conjugate. Well, not the complex conjugate, but the rational conjugate or something. The radical conjugate. I forget what that's called, but you know what I mean. This row reduces to 1 minus root 5 over 2, 1, 0, 0, 0, 0, and corresponds to, thus, lambda 2 is xy, where 1 minus root 5 over 2x plus y equals 0. Take x equal 1, then v2 is 1, and y is negative 1 plus root 5 over 2. If x is 1, then you subtract that constant to both sides. And now we have our second eigenvector. Right? So these are the two eigenvectors corresponding to the Fibonacci matrix. Then C is going to be the eigenmatrix or something, eigenvector matrix, which is 1 minus root 5 over 2, comma 1, and 1, negative 1 plus root 5 over 2. And our diagonal matrix is this. One plus root 5 over 2. You look very young, sir. What is your age? I'm in my late 30s. What's your age? Thank you. I feel very honored by that. I appreciate that very much. I'm not young. So therefore, f to the n is equal to c d to the n c inverse. Let me make sure I got the order of those right. Is it c? Yeah, d to the n c inverse. So our matrix is this. As we saw earlier, our matrix C is 1 minus root 5 over 2, 1, 1, minus 1 plus root 5 over 2 times eigenvalue negative 1, or 1 minus root 5 over 2 to the n, 0, 0, 1 plus root 5 over 2 to the n times C inverse. How do I find C inverse? I think I need to actually calculate it. I think I do need to calculate C inverse here. we calculate C inverse via C augmented I row reduced to I C inverse. So, thank you for bearing with me, everybody. I know it's a little in the weeds, but dude, I'm going to be so happy if I get this right on the first try this time. I'm going to be extremely happy. Something feels just slightly off. Okay, let's keep going for a second. 2 plus 2 root 5. I think it's fine. I think we got this. I think we're on track. want to make sure I don't make mistakes in this. Super gnarly, but now we go back to this more simple second line. And then the first line, divide the whole first line by 2. So the numerator is positive 1 minus 5, which is negative 4. So then this is negative 1 over root 5. And then divide by 2. We have 1 minus, well, let's do 1 plus, wait, no, sorry. 1 plus 1 minus root 5 over 2 root 5. So then this 1, this is 2 root 5 over 2 root 5. And then this simplifies as 1 plus root 5 over 2 root 5. Is that right? I don't know if rationalizing the denominators is a good idea or a bad idea. You're 4 factorial years old. You freaked me out for a second. I'm like, if you're 4 years old, I have to ban you, man. I can't have 4-year-olds hanging out in the chat. It's actually regulations. There are laws around this stuff. Yeah. All right. Well, you're 4 factorial. Okay. That means you're 24, right? Is that right? 4 times. Oh wait, no. 3 times 2. Yeah. 3, 2, 6. 6 times 4. Yeah, 24. All right. That's a perfectly valid age to be hanging out in a live stream. All right, so I think that this is nicest if we factor out a 1 over root 5, and then our matrix is negative 1, 1 plus root 5 over 2, 1 plus root 5 over 2, and 1. Now we have an expression for C inverse. Hell yeah. So back to our goal, which was this. We can now substitute in this matrix for C inverse. Substituting in that matrix. Well, let's make this clear. Let's just shrink this to make it fit. I'm going to factor out that 1 over root 5 to the front. Let's leave the first matrix as is. Multiply these two matrices. Negative 1 minus root 5 over 2 to the n. Here, wait. Let's match the order in which we're reading these. This is 1 minus root 5 over 2 to the n times 1 plus root 5 over 2. And then we have 1 plus root 5 over 2 to the n times 1 plus root 5 over 2 and 1 plus root 5 over 2 to the n. Okay, so this is getting a little gnarly, but remember that we are looking for an expression for Fn as n tends to infinity. Note 1 minus root 5 over 2 to the n tends to 0 as n tends to infinity. For large values of n, this is going to equal 0 because, like, why is that true? Well, root 5 over 2 is approximately 2, right? It's definitely less than 3. Which would make it more formal. So, 1 minus root 5 over 2 this is between -1 and it's definitely less than +1. I think that's good enough. So I'm going to take this term to calculate Fn. Then F sub n 1 over root 5. So I'm calculating the dot product of the second row and the first column. 1 over root 5 times -1 minus root 5 over 2 raised to the nth power plus -1 plus root 5 over 2 times 1 plus root 5 over 2 to the nth power times 1 plus root 5 over 2. There's probably some simplification I could have done earlier, but hey. And as n is large, as I just said, that tends to 0. What's going on here? Do we really have an 8? I don't remember an 8 being in this thing, but I think that terms will cancel out. -1 plus root 5. I'm going to rearrange 1 plus root 5, like use a commutative property on the first and third terms of that product, plus root 5 to the n. This would be -1 minus 5. This is 5 minus 1. This is 4. Cleaning this up, Fn is approximately 1 plus root 5 to the n divided by 2. I'm pretty sure that that's right. Come on. Come on. Did I get that right? Dang it. What? Oh, wait. Over 2. Here, I missed. I just didn't factor it exactly the way that they did. I have over 2 root 5. What? Are these where I missed some. Aha. Aha, 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 aha. I was so close. Okay, I almost did this with no mistakes today. We were so damn close. We were so damn close at the very end. This is good enough to where I say that we did it. We did it this time. Yo. This 1 plus root 5 over 2 to the n. I forgot to... I factored out that 2 and factored out this thing into 8. Okay. We're so close. So close. I want to be able to get this perfect because it's a really nice mathematical fact, I think. Trying this again. This would be 1 over 4 root 5 times -1 plus root 5, 1 plus root 5 times 1 plus root 5 over 2 to the n. Not to the 2, not squared, but to the n. And as we saw before, these two terms equal 4. So this is 1 over root 5 times 1 plus root 5 over 2 to the n. So, hell yeah. Hell yeah. All right, 1 over root 5, 1 times 1 plus root 5 over 2 to the n. We got it. We got it. We got it. Finally. Approximation hell yeah. We did it. It's been it took 3 tries, 3 streams to try to get this correct, but I did it this time. Thank you everybody for watching. I'm good. I'm done. I'm done for today. It's been 4 hours practicing math because I'm a psychopath. Thank you. Thank you everyone for watching. This has been fun today. Like and subscribe, and I don't think anybody's watching this, but if anybody is watching this, please do like and subscribe and leave a comment. It helps me a lot just to know that some people enjoy this stuff. So thanks for watching. Bye. Bye, everyone. Bye.